Okay, so we have two more categories to discuss. One is vertical stretches and compressions, and the other is horizontal compression and stretches. So again, from this chart, this is our reference. Vertical stretches and compression will take place when there is a number in the front of the function operator, depending on which function we're working with. So that's our first category to look at. So a vertical stretch is when the graph is pulled in the up or down direction. So we're going like this with the graph up and down. So in this case, I've picked the parent quadratic function. So the parent function is y equals f of x, and that's x squared. And if I was to describe in words what this transformation is all about right here, the 7 out in the front is a multiplier. So it's increasing the output values of this parent function, which is right here, by a multiple of 7. So it is a vertical stretch, and we have to indicate that it's vertical, and it's a stretch, and we should indicate by what factor. All right. So again, we can approach these problems from a graph or a table, similar to what we've done in our past notes. And if I look at the graph of the parent function, which is roughly graphed here, it's not perfect, but it'll work. If I put in these input values into the parent function, so negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0, etc. So those would be my output values. If I put those same input values into this transformed function, the first thing that happens by order of operations is the squaring and then multiplying by 7. So all of these output values are going to be multiple of 7. So we're going to, 4 times 7 is 28, 1 times 7 is 7, 0 times 7 is 0, and then back to 1 times 7 is 7, and back to 4 times 7 equals 28. So if I were to graph these new points, so x is negative 2, y is 28, that's like way up here off of my paper, my grid. And then if x is negative 1, we would have 7, so it's a little bit lower, but it's still in here. And then 0, and then 1 is at the same height, and positive 2 is at the same here. So we have pulled the graph in the up direction, which has caused it to shrink horizontally, but because the 7 is attached to the outside of the function operator, we describe it as a vertical change instead of a horizontal compression. So my observations are the y values are 7 times greater. And so what that means is my x's didn't change, but my y's changed, my y's changed by a multiple of 7. So that's the point-by-point representation of this transformation. All right, the second vertical kind of, these are non-rigid transformations because the shape is changing instead of just a translation left to right or flipped over the x-axis or y-axis. So it's the same kind of logic for a shrink, but instead of pulling the graph apart, we are squishing the graph down. So again, the parent for this example is still y equals f of x, is the quadratic function. And in words, what is this 1/7 doing? It is a vertical compression. And that is because the number 1/7 is, the absolute value of 1/7 is less than 1. All right. So sometimes people will say a vertical stretch by 1/7, and you generally get the idea. But here again, this is off of this chart. So when the value attached to the function operator is between 0 and 1, absolute value of this number is between 0 and 1, it's a vertical compression. And what happens is all of the input values stay the same, and our outputs are multiplied by 1/7. So we end up with some crazy fractions, 4/7, 1/7, 0, 1/7, and 4/7. So it's a little harder to graph. You can imagine that in here, so we got 0, 0. At -2 and +2, we have 4/7. So imagine in here that there are 7 little tick marks. 1, 2, 3, 4, 5, 6, and then 7. All right. So at 2, it's 1, 2, oops, 1, 2, 3, 4. So roughly like this, and like this, about the same height, and then 1/7. So it's like in here. So basically, it's like somebody stepped on the graph and flattened it out. So it's a vertical compression. All right, again, it looks like a horizontal stretch, but because the number is attached to the function operator, meaning it's outside or after the fact, we describe it as a vertical compression instead of a horizontal stretch. So y values are changed by a multiple of 1/7, and the x values remain the same. So again, what does that look like if I consider every single point on this parent graph? So this is my original graph, very roughly drawn. Every single point, the x value stayed the same, and the y value is 1/7 as tall. So that's it for vertical and compressing and shrinking. Okay, so our last category, finish up these videos, are horizontal compressing and stretching. Again, this is our reference chart. This time around, the number is attached to the x instead of being on the outside of the function operator. So it has an impact on the x and not the y. So if we look at this graph, this transformation function of absolute value of 7x, the parent is the absolute value function. And in words, the 7 causes a compression. Remember, when anything is with the x, kind of behaves in the opposite of what you expect it to be. If the absolute value of that number is bigger than 1, it's a compression, not a stretch. But again, this chart is here for your reference, and you should have a copy of that in your notes. So we have a horizontal. We have to indicate in which direction, horizontal and vertical, in the type, compression. And then by how much? By 7. All right, sometimes people will call it a horizontal stretch by 1/7, but either way it's correct. Okay, so I have plotted part of the absolute value graph, but not all the way out to my table of values. I picked -14, -7, and 7 and 14 because those are multiples of 7. It was a little bit easier to explain what is going to happen. So, looking for a cover sheet. All right, so basically, in order to get an output value of 14, for this right here, we only need an input value of -2. So -2 put into this function right here would be 7 times -2, that's -14, absolute value, that is 14. Okay, because I know that it's a horizontal change, I know I'm going to have new x's instead of new y's. Likewise, if I use a -1 as my input right here, 7 times -1 is -7, absolute -7 is 7. So that would give me an output of 7. 0, there's no change. Similarly, in order to get an output value of 7 on this side, I only need a 1, and then I only need a 2. So again, I knew we were changing the x's because it's a horizontal transformation, not a vertical. So what are my observations? My observations are my y values stayed the same. And the x values are 1/7 of the original x values. So understanding in words what's happening, and that's a lot of words to write, simply that every single point, the x values are going to be 1/7, all right? And then the y values stayed the same. So that's a horizontal compression. Okay. Last one is a horizontal stretch. Oh, sorry. Let me get this so that it matches up with your notes right here. So in your notes right here, it says x over the b. Well, the b is 7. So this is equivalent to x over 7. Sorry to confuse you. So 1/7 is the same thing as x divided by 7. Matches your table a little better that way. All right, so last one. This time we have horizontal stretch. So again, referencing the table, everything comes off of this little chart. And this time the parent is still the same absolute value graph. And we know that we are changing the x's because the 1/7 is attached to the x. It's inside of the function operator. So we're going to have a horizontal stretch. We have to indicate if it's horizontal or vertical. And then the type, it's a stretch. And then by a factor of 1/7. All right. Sometimes people describe it in terms of a compression. If you get this part right here, I'm a happy camper. All right, so what's going to happen? Well, instead of using my input values of -14, -7, 0, 7, and 14, I've got to think about what new values I would have. Okay, so to get an output value of 14, all right, I need to have an input value that was bigger than what I started with. So this time, instead of division by 7, we're going to multiply by 7. All right. So if you put this right here into this function, basically we'll do scrap work right here. I'll show you what that looks like. So if I put in, I've got 1/7, and if I put this in as my input, so -14 times 7, and then the absolute value. Well, this 7 and this 7 divide out. So you end up with the absolute value -14, so you still get 14. So all my x values this time, instead of being division by 7, it's multiplied by 7. So -7 times 7, and I'll still get an output of 7, 0 is 0, and then 7 times 7, and I would still get an output of 7, and then 14 times 7, and I'd still get an output of 14. Oh, I thought the timer was up on the video. Okay, so what are my observations? My observations are my y's stay the same. But my x values are 7 times bigger. Okay, and so point by point, basically we're taking every point that's on this parent graph and changing them in this way. So my x values are getting changed by 7 times my original x. My y's stayed the same. So the b, if you look at your chart, our b was 1/7. So this is the same thing as saying x divided by 1/7. So either way, you can write it like this, or you can write it like this. Written this way is what your chart uses. But this might make more sense to you. Okay? All right, that's all of the transformations. Hopefully these videos help.